Hey everyone, Sean here for Lambda School, and in this video we're going to be looking at the linked list data structure. So first off, the objective to keep in mind as we go through this video is that we're going to try to understand how linked lists work, at least initially at a conceptual level. So as we go through this video, I want you to try to start building up this mental model of how what a linked list is, as well as how a linked list works, at least in your heads. And then when it comes time to actually implementing it in the project, that's where you will take that mental model of how a linked list works and translate that into working code. And that's really where you get to see and experience the real world engineering trade-offs that have to be made when you're actually implementing data structures. So first off, let's talk about how we might think about a linked list, or how we might represent it in our heads. So a linked list, very much like an array, is used to store lists of values, except a linked list does it a little bit differently from an array. So with a linked list, the most fundamental difference between a linked list and an array is that linked lists store each element as an isolated node, which is represented by the circles here. So we have these values, these three values that were being stored in our linked list example, 12, 39, and 5, and we can see how each one is essentially isolated in its own node, with the only thing connecting the nodes are these arrows, in this case, these arrows represent references from, for example, 12 pointing to the node that contains 39, and then the 39 node has another reference that then points to the next node in the list, the node that contains the element 5. And then at the very end of the list, we see that the node that contains 5 points to n, which in this case represents none or null, which is the indicator to show that 5 is the last element in our linked list. So let's really quickly contrast this with how we might draw out or represent an array. Again, an array is also used for holding lists of values, but it does so in a contiguous fashion. And what I mean by that is that to store elements in an array, you essentially have this contiguous block of memory that can hold up to a certain amount of items, or has a certain amount of space that it has essentially pre-allocated. So in this case, we're assuming a static array instead of a dynamic array. And so in this example, we have the exact same elements, the exact same number of elements as well, 12, 39, and 5. And here in an array representation, we don't really think about the elements as being isolated inside of their own nodes. While it is true that each has its own slot in the array, we don't really think of them as being isolated, right? So 12 essentially sits right next to 39 in this contiguous block of memory. Another important thing to note with this static array representation that I'm showing you here is that if we look at this picture, this array has space for 7 items. So there's the first 3, 12, 39, and 5, and then we see an additional 4 spaces after the 5 for 4 more items if we chose to put them in there. So essentially a static array is pre-allocated with a certain amount of space up front. And actually, this is going to be, as we'll see, one of the main trade-offs between a static array representation to hold a list of things and a linked list representation to hold a list of things. Anyway, back to the linked list representation, a couple of terminology, or a couple of terms we might want to use here. So the first node in the linked list, the 12 in this case, the very first element in the list is denoted as the head of the linked list. Conversely, the 5, the last element in our linked list, is denoted as the tail. Okay, and then here we're also just showing that 39 as well as 12 and 5 are all just values that are stored in these nodes. And then the n at the very end here just represents null or none, again indicating that 5 is indeed the tail, right? So again, the tail is defined as the node in the linked list that points to none. And there should only be, at any point in time, one single list node that actually points to none. Every other linked list node should point to the next node in the list. So let's give a real quick pseudocode example of what this node class might look like. So here we've talked about how the node class holds a value. So we'd have a self.value or this.value being set to the actual value, and then this other property next that is the reference that points to the next node in the list. And if we have a node instance that is the tail of the list, that's not actually going to refer to another node, it's just going to point to none. Okay. Next up, let's really quickly look at what the actual linked list class itself might look like. So the linked list class is actually just going to comprise of the head and tail references. So as far as the linked list is concerned, it is just going to refer to the head of the list and the tail of the list. So an important thing to notice here is that from the linked list class's perspective, it doesn't have direct access to any of the nodes in the middle of the list. We can start from the head, and if we want to, for example, iterate to some node in the middle of the list, you'd have to start from the head and kind of work your way down from there. Likewise, the tail gives us fast access to the very last element in the linked list. What's also important to notice is that when we've been drawing out the linked list and it had these arrows, those arrows indicate a kind of direction as far as the linked list is concerned. We can go from the head, and from the head we can refer to the next element in the linked list. But from the second element in the linked list, at least with our current linked list representation, the second element in the linked list has no knowledge of the previous node that referred to it. In this case, the second node in the linked list is not able to go back to the head. Likewise, the tail of the linked list is not able to refer back to the second to last element in the linked list. And again, with our particular linked list representation that we're talking about here in this video, this is true for every single node in our linked list. So generally speaking, no node is able to refer to the previous node. Each node is only able to refer to the next node. Okay, so from here, let's go and walk through an example of how we might add a new element to our linked list. So let's say we have an insert method on our list, and we go and call that insert method and pass it a value 15 in this case. So we're looking to add the value 15 to our linked list. So the way we'll have this work, and here we'll have our initial starting state. So our initial linked list with 12, 39, and 5, with the head being 12 and tail being 5. First thing we're going to do is we're going to go and wrap the value 15 in a new linked list node. And by default, we can just have that point to none as well. And the reason for that is because typically when we add to a linked list, at least when we're going to go and add a new value to this particular linked list, we're going to always add it to the tail. It'd be a bit slightly different if you wanted to go and add it to the head. That is indeed possible, but in this case, we're going to assume that we are inserting the new element to the tail of our linked list. So 15 is essentially going to become the new tail, and as a result, because we know that, we can just, as we wrap it inside of a new node, let's just already up front have it point to none in this case. Okay, so we wrap 15 in a new node, have it point to none, and then the next thing we have to do is we need to go and move 5's pointer, move 5's reference. So 5 initially pointed to none as well, and the next step that we need to perform in this insertion process is to go and take 5's reference. So 5 has a self.next, which before pointed to none. In this case, now we need to have self.next on the 5 node point to the node that holds 15. And so once we've done that, voila, we have our new linked list with the newly added element. And from there, we need to go and also not forget to change the linked list's tail reference, which initially was pointing to 5. We need to move that to now point to 15, since that is the new tail of our list. That is now the current element that points to none. So it's the very last element in our linked list. So that's just a really quick rundown of how we might go and insert elements into our linked list. So obviously that wasn't everything we need to know regarding linked lists. So here are a couple of questions you might want to ask yourself in order to think about some other details and some other concepts that pertain to linked lists. So again, we talked about inserting an element into a linked list that already had some elements in it. So another edge case you might want to ask yourself is, how would we have to change this flow if we wanted to insert an element into an empty linked list? Right? So what would the initial state of our linked list look like if it was entirely empty? Likewise, what would our linked list instance look like if it only had one element in it? How would the process of inserting another element into a single element linked list change from what we just saw? Additionally, how would we actually iterate along a linked list? Again, we talked about this a little bit earlier, but how would we actually iterate along a linked list in order to reach an element that is not the head or tail of the list? Right? Because again, with our initial linked list class, the example code we gave a few slides ago, we saw that the linked list class only has direct access to the head and the tail of the list. So again, you want to ask yourself, how do we actually go and reach any of the other nodes in the list? Lastly, how would you delete or remove an element from a linked list? Okay, and then lastly, let's talk a little bit about some of the pros and cons of linked lists. So we've talked about some of these already, but let's go and actually list them out here. So unlike arrays, and indeed most of the comparisons that we'll make when we're talking about pros and cons of linked lists is going to be in contrast with arrays, again, because they serve very similar purposes, but at the same time, arrays and linked lists do have very distinct trade-offs. So one of the pros of linked lists is that it's actually easier to insert and delete from the middle of a linked list compared to an array. So here in this case, we're not talking about inserting to the end of an array. We're talking about if we already have an array of elements and we want to specifically insert into the middle or even into the very front of the array, a linked list is actually going to do that better. And if you don't understand why yet, you'll kind of want to think about why that is the case. So I would encourage you to kind of draw and model that out, right? So to draw out inserting to the beginning of a linked list, and then draw out inserting to the beginning or the middle of an array, likewise, and see what needs to change or how both data structures do it differently. And then you'll kind of get an idea of what the pros and cons of both of these data structures are with regards to inserting and deleting from a linked list or an array. Okay, so one of the cons then of linked lists is actually that linked lists are not as cache friendly as arrays, because caches are actually optimized for contiguous memory accesses. And as we've already talked about, arrays are indeed just contiguous blocks of memory. So the items are all literally stored right next to each other in memory, and caches are optimized for accessing memory addresses that are actually right next to each other. The structure of a linked list does not at all guarantee that the different values of the linked list, even though we might have a linked list node and the next node in the linked list, even though as far as the linked list is concerned, they are quote unquote right next to each other, we are not guaranteed to actually get them stored contiguously right next to each other in physical memory. And so linked lists in that sense are actually not as cache friendly as an array is. Again, due to the contiguous nature of arrays. And then lastly, we also talked about this a little bit when we were looking at the static array representation, which is pre-allocated a certain amount of memory. Linked lists do not need to be allocated memory up front, unlike a static array. Therefore, unlike a static array, with a static array, once you hit the end of the array, more memory needs to be allocated. And that actually turns out to have a lot of overhead associated with it, a lot of extra work that needs to happen in order for that additional memory to be allocated so that additional elements or items can be added to that static array. Linked lists actually do not exhibit this particular drawback. So it's actually a lot easier to just keep adding elements onto the end of a linked list without having to worry about how much space we have allocated to that linked list. Because again, all a linked list is concerned about when we're adding a new element is it just needs enough memory to wrap that individual new element that we're adding inside of a new node, and then we have the old last node in the list reference the new last node in the list. So the references are not taking up any additional memory. We just need memory for the individual elements to get wrapped in linked list nodes, which is again different from how a static contiguous array stores elements. So that's it for this video. We talked a little bit about how to think about linked lists, as well as a bunch of questions that you might want to ask yourself in order to better flesh out your mental understanding or your conceptual understanding of linked lists. And we talked a bit about pros and cons. So make sure to write down any questions you have or any questions you thought of as you were going through this video, and be sure to ask those questions when we get to the live lecture. Thanks.